Good morning, everyone. So welcome to the second week of IVC, International Virtual Course in Astrostatistics and Machine Learning. So I will be your host this morning. This morning, we will have two sessions. One is on Introduction to Machine Learning, and the second one is on classification. So our first lecturer today, who will give the topics on Introduction to Machine Learning, is Assistant Professor Jakramate Bootkrajang from Chiang University, Department of Science. So Dr. Bootkrajang obtained his BS Bachelor in Computer Science and Master in Computer Science from Seoul National University, and then he obtained his PhD in Computer Science from the University of Birmingham in 2014. So I will give the time to Dr. Bootkrajang. So please start. For the student, you can ask a question anytime. Please raise your hand and I will ask you to switch on your video to ask your question. Thank you.
Okay, thanks a lot. Right, so let me first share my screen. Oh, by the way, thank you for the brief introduction to myself. I didn't remember that I gave away such information, but that's very kind of you. Sorry, I just need to change. Right, just some tests so you can see my screen now. Okay, and my voice is clear, hopefully.
Yes.
Okay, cool. Yes, so thanks again for the invitation. Okay, I must say that I accept the invitation without hesitation because I'm also interested in applying machine learning to astronomy data, although I'm quite new to astronomy, but I'm willing to learn as well. So my background is more or less about machine learning, okay, but in synthetic data sense, okay, I develop algorithm and test it on some artificial data, and it would be nice to get my hands dirty on real world data, okay, and I'm from, as I said, I'm from Department of Computer Science, Chiang University. Okay. So again, if you have any questions or unclear parts during the talk, please feel free to raise your hand and interrupt me. Okay. Right. So so this talk is going to be like a really general overview of machine learning. Okay, basically, we would like to, I have this objective. Hopefully after the talk, you should be able to at least answer these three questions. Okay, the first one is we want to understand what machine learning is, okay, in general concept. And of course, basically, there are three paradigms within machine learning field, okay, for which we have supervised learning, unsupervised learning, and the other one is reinforcement learning, okay. But I think what would be mostly useful for astronomy astronomical data is supervised and unsupervised learning. So we'll be focusing on these two types of learning paradigms. All right, and after the talk, you should be able to differentiate between what is supervised learning, how is it differ from unsupervised learning. Okay, and lastly, I'd like to kind of introduce the whole process of doing machine learning. Okay, what is the first step, the second, and so on. Okay, I think that we can summarize the whole process into about 6 different steps. All right, so these are the main goals of this talk. Okay. Right. So let's start from the outline. Okay. I will start with some motivation as to why we need machine learning in astronomy. Okay. And then we'll talk about the data itself and the model. Okay. For the data, we probably need to talk about feature extraction as well as feature selection if needed. Okay. And then we'll move on to models and the learning part. Okay. The big question here is that what does it mean to learn a model? Okay, how learning proceeds in machine learning. Okay, and then we move on to the first paradigm of learning, which is supervised learning. Okay, 2 major representative tasks from supervised learning is obviously classification and regression task. Okay, and then we'll see the second paradigm, which is unsupervised learning. The representative task for this unsupervised learning is probably clustering. Okay, data clustering. Okay, and then we will move on to the regularization of the model. Okay, this is the purpose of regularization is just to encode our bias or belief of the data into the model. Okay, this helps us a lot when we haven't got enough data to fully train the model. Okay, finally, we'll talk a little bit about evaluation of the model, and as well as challenges in machine learning and the summary. Okay, so so the talk will last about 1 hour and 10 minutes, I guess. Okay, right. So before we begin, I would like to start with some motivation. Okay, so this is more or less similar to what I am collaborating with some researcher from NARIT. Okay, say for example, if you like to detect stars in this image of several stars. Okay, I guess from what I've learned from astronomy is that there are several types of objects in this big image on the right hand side. Okay, but what we are particularly interested in is this guy. Okay, I guess I've got it right. This is a star, and as you can see from well, you as an expert in astronomy can see from the big picture that there are quite a number of stars in this picture, and we want to detect it. Okay, so traditionally, I believe that the detection of stars would require expert, okay, with some knowledge on astronomy to manually inspect the image. And for some reason, we then detect that these, for example, these are stars that we are looking for, okay? But the problem is, as you can imagine or experiencing yourself, that this is quite time consuming, okay? This is just one image, and I guess you have several maybe millions of these sort of image, okay? And probably you do not want to detect only stars, but some other objects in the sky, okay? That would be also interesting, okay? So the question nowadays is, can these tasks be automated somehow? Okay, can we write a program to simply scan the image? All right, we can move from top left to bottom right, no problem, or top right to in what direction that you would like to perform, okay, and come up with some computer program to actually scan and detect stars or whatever objects that you are looking for in the sky, okay? And turns out that, well, it is possible, okay? So you can construct rules, well, based on some your knowledge on stars, okay? So this is just, for example, if we look at a window of smaller image, okay, and for example, this is not precise in by any means. For example, if we look at say x dimension, and if the light is the length of the pixel which represent light is greater than 25, okay, and in y dimension is greater than 20 pixels, okay, and you probably said this is star, or else this is not star, okay. So so this is just arbitrary rule that I made up, okay, but just to serve the point that we can actually construct this kind of rules to actually detect whatever objects in the sky that we want to look for, okay. But the problem is, as I would like to point out, is that, well, as you can see, this is very basic rule, okay. Probably you have some more complicated rules other than this, and just for the sake of detecting the stars more accurately, okay. But as you append some extra clauses in the if statements, okay, you would end up with, I'm not sure, but I guess it's going to be more and more complicated, okay, and afterward it's going to be difficult to maintain, okay. We need to look at every clauses in the if, and if you have else if, okay, it's going to be a nightmare to maintain, okay. And the other thing is that it might not generalize well to new objects, okay. Of course, it might be able to do well on something that we have known of, but if some new objects or stars appears in the sky, okay, and that the expert have no idea what kind of star that is, okay. I'm not sure if I said it correctly, but suppose there is new object appears in the sky, okay, this particular rule that we have construct, okay, and maintain might not be able to distinguish the new object, okay. That is to say, it is not adaptable to the data, okay. This is I guess currently many of us are using this rule-based approach, okay. But now, since we've seen that there are some disadvantages of this rule-based approach, we ask further, can we do better, okay, and how? All right. So that leads to machine learning approach, okay, for which we have a machine learning algorithm or model, okay, in the middle, which tries to capture the relationship between the input and the outputs, okay, whatever they are. So suppose in our star detection example, the input should be something like this. It's a window of one particular object in the big picture, in the big image, okay? And then we feed it in to the model in the middle, okay? And it does some sort of calculation and prediction, and it outputs whether or not this input is a star, okay? So the output is yes and no, okay? And of course, this guy in the middle, the model, has to learn this relationship between input and outputs. And we need lots of examples, I would call examples, of input and output, so as to train the model to be able to differentiate between stars and not stars objects. Okay, and this is probably the approach that we are aiming for nowadays. Okay, I'm not sure if it's I mean, it would be applicable in every situation, but we'll see when to use machine learning, when to not use machine learning. Okay, right. So any questions so far? Okay, cool. Right. So let's summarize. Okay, what is machine learning from the example? Okay, broadly speaking, machine learning is the study that includes design and analysis itself, okay, of algorithm which gains expertise. Okay, this is keyword. It should gain expertise in some tasks using past experience. So past experience is in the form of data. Okay, like you collect a lot of input output data, okay, and you throw it in for some algorithm to learn the relationship between input and output, okay, and then hopefully it will be able to learn the patterns, how this particular kind of input is associated with this particular output. Okay, if you have lots of data, the algorithm should be able to pick up that relationship. Okay, so mathematically, machine learning aims to capture the relationship or function, okay, between the input and the output that we want. Okay, and what's learning, by the way? So when we see that this machine learning box is one kind of function which takes as input, for example, the image, and output binary variable, yes or no, okay? And you can see that this function has parameters. The learning is actually the process of estimating and adjusting these parameters to best fit the data. Okay, so this is the word learning in machine learning. Okay, it means adjusting parameters. Okay, and the next question is, how do we adjust the parameters? Okay, there are several sort of stuff, but mostly it is based on optimization theory. Okay, all right. So so the next important question before we jump into the conclusion that, oh, the machine learning is great, let's use it whatever in all situations that we have. Okay, well, interestingly, that is not the case. I mean, not all scenario that we should use machine learning. Okay, so the question is when to use machine learning. Okay, probably there are, in general, there are three cases when we might consider ourselves using machine learning. The first scenario is that when humans are not able to explain their expertise. Okay, so this is interesting. It relates to how our brains works and how we know very little about brains at the moment. Okay, when, say for example, when we try to when we ride a bicycle, okay, we know how to ride a bicycle, but we cannot explain the process of riding a bicycle precisely in the form of algorithm. Okay, we just know that how not to fall down. Okay, fall down, and to write it in a precisely that algorithm that we can turns it in a program, that is, I think, very difficult. Okay, we know how to do it, but we don't know how to describe our expertise. Okay, this is also true for image recognition. Okay, like when we walk out of the building and see the first person. Okay, and we can tell instantly if that person is male or female, but to write a program to recognize the image of male and female would be extremely complicated, okay, and difficult as well, right? In such case, I guess the best way is probably to make use of machine learning to help us capture such relationship between input and output, okay, without sort of going into the details how to actually differentiate or how to actually describe the algorithm behind that logic of decision making. Okay. The second one, the second scenario where I think machine learning is appropriate is when human expertise does not exist. Okay, this sounds weird. Okay, but for example, this is widely used example where human expertise does not exist in fraud detection. Okay, say you have some sort of transaction, and you as a human doesn't even know if there is a fraud within the transaction, but in hope to detect such irregularity, machine learning has been used to detect weird pattern of transaction, and that's, I guess, the second scenario where we should consider using machine learning. Okay, and the last scenario is quite obvious, is that when your solution changed in time. Okay, as I said earlier, we could have a rule base for detecting stars, but what if we have new stars or new objects in the sky? We need to re-implement the whole rules, okay? And that could be like time-consuming, error-prone, okay, or whatever obstacle that we would face during the construction of the new rule set. Okay, and would it be better if our algorithm can adapt itself to the change of the data? Okay, and so that it stay like up to date to whatever data that we have in hand. Okay, so this is probably three cases that we might consider using machine learning. Okay, And what's the opposite situation? For example, if you want to do sorting or something that we already have a good algorithm to do those sorting, searching, some sort of stuff. Okay, we then use whatever algorithm that we already have. That would be better. Okay, so using machine learning in the case where we already have a really in terms of in computer science, we say that we have polynomial algorithm. Okay, it's fairly efficient algorithm to solve the problem already. We should adopt those algorithms instead of trying to apply machine learning. Okay. Right. So let's decompose the three players in this diagram. Okay, input, model, and output. Okay. So of course, the most important thing before we try to apply machine learning is probably that we need to have some data. Okay, and data is in the form of input mostly, and with output for the supervised learning. Okay, but basically we have three components, major components in machine learning. You have input, could be image, could be signal, okay, it could be a text, right? And in whatever form, it has to be converted into a vectorial form or appropriate form for the model to make use of such data. Okay, and the second component is the model itself. Okay, and the selection of model reflects our understanding or assumption about the relationship. Okay, if speaking in terms of mathematics, if the relationship is linear, we could use linear model to capture the relationship. If it's non-linear, then we should switch to non-linear model. Okay, and lastly, the output. Okay, this depends on the task. If you have star detection, your output would be yes or no, it's binary variable. If you want to further classify stars into different categories, you probably have multiple, we call multi-class outputs, okay, starting from 1 to whatever number of classes that you have, k. Okay, if you are concerning with regression model, your output would be real value numbers. Okay, if you are concerning with grouping similar data together, which is essentially the idea of clustering, you would have cluster assignments as the output. Oh, sorry, the output of the model, but not the output that you need to prepare. Oh, we'll talk about unsupervised shortly. Okay, but yeah, so these are, I mean, from application perspective, you probably need to concern about inputs, model, and outputs. Okay, and we'll see afterwards how they interact with each other. Okay, so I will start from the input. Okay, basically is to prepare your data so that it is in some suitable form so that we can feed it to the model. Okay, and probably the keyword for input data preparation is feature extraction. Okay, because normally the data that we have doesn't in the suitable form for the model to learn from. Okay, mostly model expects vectorial data, vectorial representation of data, okay, a vector of numbers, okay, and we need to somehow construct such representation of the data for the model. Okay, so this is but just an example. Okay, say for example, if we have this light curve on the left hand side. Okay, this is the visualization of the light curve of some stars, I believe. Okay, and then we need to convert this into a vectorial representation of data. Okay, and I believe this is my joint work with Dr. Tesha Angkun and Dr. Nahathai, and Dr. Shuttipong as well. Okay, so this, I believe we have used feeds Python package for signal feature extraction. Okay, and it produced like loads of features. For example, it extracts amplitude. Okay, some of which I don't even know what they are. Skewness. Okay, mean of this signal intensity, right? And I think we have from feeds package we obtain about 600 something of light curve features. Okay, and from that we also do feature selection. Okay, which I will talk about later on. Okay, anyhow, so this is the first probably the first process in machine learning, that you need to prepare your data by performing feature extraction. Okay, if your feature extraction is more complicated than this, people also call feature engineering. Okay, and the intuition is that you need to look for the most informative features, or extract the most informative features from your data, so that the model can learn about the relationship better. Okay, if your feature is poor or non-informative, then the model would not be able to associate the input with the output that you want. Okay, so this is crucial step. Okay, and it is the first step in the process as well. Okay, right. So let's see some more example. What if your original data is image? Okay, large image. How do we extract features? Because there are several feature extraction methods for image data, but the most basic approach, it would be to divide the whole image into a grid. Okay, and then you take a look at each element of the grid in turn. Okay, and from these, for example, we got a smaller image. Okay, from this large image, and from these we probably just concatenate them. Okay, horizontally or vertically, that's fine. Okay, for example, this is just a raw pixel value from this image. You got red channel, green and blue. Okay, I believe that from the telescope, you've got more channels than this, but this is just example. Okay, you stack them into a vectorial form. Okay, you can normalize your input so that the values are between 0 and 1 as a convention, and that we normally do. Okay, and that would be your representation of this small image. Okay, right. So I'm not going to go into details of how to actually extract this visual features, but I'd like to point out the keyword, okay, that feature extraction is important as the first step to do machine learning for preparing your data. Okay, right, so let's skip the model for a bit and jump to the outputs. Okay, for the outputs, as I said earlier, for regression, we would like to predict real value outputs. Okay, for example, if I were to try to relate regression to our star detection problem, would be to predict the, for example, coordinates of stars within an image, okay, or the size of the stars. Okay, that's also possible. And for regression, we have real value outputs. Okay. Whereas for classification and clustering, we have discrete value outputs. Okay. For classification, we want to assign class level. Okay. The level is just to indicate which class of object this input belongs to. Okay. And for clustering, it is more or less similar, but we, instead of calling this output class level, we call cluster assignments. Okay, and this assignment should group similar objects together. Okay, we will see this shortly, and this is basically the output. Of course, there are many other outputs that it depends on how would you like your model to produce the output. Okay, some would want to the model to output the actual some structural outputs. Okay, for example, in drugs discovery field, okay, they want output to be actually the structure of some molecules of the drugs that they are studying. Okay, so so the output is not confined to these two types of outputs, but these are the most commonly seen outputs in machine learning. Okay, but it depends on the task, if I would say. Right now, let's we have the input and the output. Okay, input, you need featured section or some preparation to make your input into the vectorial form so that it can be fed into the model. For the output, it can be anything that you want the model to make the association between the input and the output that you want. Okay, so if I use this letter X to represent input, okay, I try to boldface it so that it represents that X is a vector and Y is some scalar. Okay, so mathematically, the model is just a function which maps X to Y. So X is from the input space and Y is from the output space. Okay, and you can define X and Y in whatever ways that you deem fit to your problem at hand. Okay, and of course this function f has parameters that need to be tuned. Okay, and we will tune or estimate or approximate these parameters using the data that we have. Okay, for example, I think you have seen a regression problem last week. Okay, so you may have recalled that this is a basic form of linear regression. Okay, this function f, okay, receives input x, okay, and the function itself is parameterized by w it is a vector, okay, and of course W transpose X, okay, this dot product would produce your output Y. Okay, so the mapping that you are using here is a linear mapping from a space of X to the space of Y, or the output. Okay, and of course this W we need to tune or adjust so that it somehow captures the relationship between X and Y that we have. All right, so when we talk about the function being able to capture the relationship, how do we measure that quantity? Okay, so normally we use what we call loss function. Okay, the loss function would quantify I would say the goodness of fit of the model to the data. Okay, and for different tasks, we have different loss functions, as I would show you in these slides. Okay, so let's carefully have a look at these loss functions one by one. Okay, so for the classification task, okay, the idea is that you would like to associate the input to the class that this input belongs to. Okay, and the model should be able to predict or tell in which class this object xi belongs to. Okay, so this is our, so f of xi parameterized by theta is our function, classification function or model. You can think of it as a model. Okay, and the loss is actually if the function assign xi to other classes, to classes other than the class that xi actually belongs to, which I use yi in this case. Okay, so yi is the correct class level, but if the prediction is not equal to the correct class level, then it incurs loss. All right, so this one is a identity function which returns 1 if this clause is true and returns 0 otherwise. Okay, so if they are not equal, then we got 1 from this function. Okay, and if we sum over all data that we have, okay, from 1 to n, capital N, then we have a total loss of this model F. Okay, and as you can see, the larger this loss is, the worse the model performs. Okay, and we want to minimize this loss. Okay, we want to make it as small as possible. Okay, and that's where the optimization comes in. This is for classification. Okay, pretty straightforward. Right, we normally use this L as the notation for loss function, but that's probably just not the standard. Anyhow, so how about the regression? Okay, regression, we also have square loss. Okay, in regression, right, I think this is, I made a mistake. Has to be in the same form. Sorry, it has to be f of xi parameterized by theta, some regressor. Okay, and this has to be the output of the regressor. Okay, and for regression, we want to actually quantify the mismatch between the prediction and the true value of or the true target. Okay, people could call it target. Sorry if I need to fix this. Okay, so it has to be in the same format as this f of xi parameterized by theta. Okay, and also we sum all over the data in our data set. Okay, just to see how well it performs. Right, and for the clustering, we also have more or less loss function as well. Okay, for example, this k-means clustering. Okay, the aim is to group the data into clusters. Okay, for which the clusters are represented by the cluster mean mu. Okay, and this z vector, this is a vector, indicates the cluster that this xi belongs to. Okay, so zi is from 1 to k. Okay, so this is just to say which cluster this xi belongs to. Okay, and the assumption of clustering is that the cluster that the algorithm found should be compact. By compact, it means that this xi should be as close to mu, or the center of its cluster, as much as possible. Okay, and the square is just to get rid of the negative and positive sign. And if we sum over all data in our data set, this should be minimized as well. Okay, well, subject to the constraint that we need to form k clusters. Right. Okay, any questions? Am I going too fast or too slowly?
Is there any question from the participants?
Okay, so I take silence as no. So let's move on. Right, so okay, so it's 9:50. Right, so let's summarize a bit about machine learning paradigms. Okay, we've seen examples of classification, regression, and clustering. Okay, so as I mentioned earlier, that's actually there are three paradigms in machine learning: supervised, unsupervised, and reinforcement learning, for which reinforcement learning we will not talk about in this session. But for supervised learning, okay, the characteristic of supervised learning is that when we train a model, okay, we provide in the form of data, okay, the inputs and the correct outputs. Okay, so these correct outputs will be used to help us adjusting function parameters so as to minimize the loss as much as possible. Okay, so data comes in as input and output pairs. If it's classification, you need a picture of a star, as well as the answer or the output, which indicates which class of star classes this input belongs to. Okay, you need both input and output. Okay, and from this you can use these pairs to minimize the loss in whatever task that you are trying to perform. Okay, with a classification or regression. right? Whereas in unsupervised learning, there is no correct outputs. Okay, what you have is just the input, and you somehow try to incorporate some explicit constraint. Sorry, not implicit constraint, so as to evaluate the performance of the model. Okay, as in clustering, normally you don't have output which indicates which cluster this input belongs to. Okay, you leave it to the model to try to figure out how should the data be grouped. Okay, and once they are grouped or the cluster, you can then measure the performance according to your evaluation criteria. Okay, and from this perspective of having output and not having output, so unsupervised learning seems to be a little bit more challenging, okay, if not more difficult than supervised learning. Okay, and of course, for unsupervised learning, okay, the output can be something which could deviate from our understanding. It could discover something new that we haven't known about or known of. Okay, right. So the difference again is in the nature of the learning. Okay, in supervised learning, you have correct answer to guide your model towards the minimal loss, whereas in unsupervised, you don't have such information. Right. So let's have a closer look at the classification task. Okay, we want to infer function f, okay, which maps from input to output. X is, as usual, feature vector, and y is discrete output or class level. Okay, using the data that we have. The data should be input and output pairs, right? So we the aim is to minimize the 0-1 loss. Okay, so data is in this format, feature vector, and the correct answer of where this feature vector belongs in the set of classes that we have. Okay, so we have binary classification for which the outputs can be 0 or 1 or -1 or 1. Okay, there are binary classes outputs, or you can extend this to multi-class classification. Okay, recently people also start investigating multi-label classification. Okay, for which one object can belong to more than one classes. Okay, and that's what we call multi-label. Okay. Also, the detection task is also binary classification task with special interest in one class only. Okay, if let's say, for example, we want to detect some rare events in the sky. Okay. Yeah, there are examples of classification models that I'm not going to be able to go into details, but I guess we have these 4 families. So I think probabilistic, okay, you have Bayes classifier, logistic regression, or if you want to go through tree-based, you have decision tree, okay, an ensemble or a collection of several trees. We have random forest. We could also perform boosting on trees. Then we have gradient boost tree, okay, and etc. etc. We also have support vector machine, which operates, which builds on geometrical assumption that the best decision boundary, this blue line should be the one that has maximum margin. Okay, and of course nowadays we're crazy about neural network and deep learning, convolutional neural network. Okay, this is another I would say family of model. Okay, anyhow, these are examples of classification models. Okay. Right, so let's see some example before I run out of time. So for logistic regression, okay, this is, oh, by the way, there's the 0-1 loss that I mentioned earlier. That's how you count wrong prediction or misclassification, but the function itself is not continuous, and therefore it's difficult to optimize. And therefore, these models use different loss function, which is actually the approximation of the 0-1 loss. Okay, for logistic regression, we have log loss. Okay, negative of log of sigma is the sigmoid function. Okay, y is encoded such that it has value plus and minus 1 for binary classification, and the w is actually the parameters of the model. Okay, whenever the sign of w transpose x agrees with y, okay, if y is minus, this dot product should produce negative value. If y is plus 1, this should produce positive values. Okay, and in such way, this quantity will be minimized. Okay, and the objective is actually minimize this loss function by adjusting this model's parameter. Okay, of course we can use calculus. You differentiate this objective with respect to w, and then you perform these gradients based learning update rule. Okay, this lambda is what is known as learning rate. Okay, it controls how much we adjust w. Okay, so wi plus 1 is the next iteration. This is the current value of w at iteration I, and we want to update it in the way that we add some small amounts of gradient to this w. Okay. So regression is quite similarly. We need to infer function f from x to y, but y is real value target. Okay, and we want to minimize the square loss. Data comes in as feature vector and target. Okay, I use target instead of class level to explicitly indicate that this is not discrete, it's real value. Okay, this is also supervised learning. The model for linear regression would be w transpose x. The loss, okay, this is the correct one. The square loss, okay, and the objective of the regression task is to minimize the loss, okay, by adjusting this parameter w, okay, and the optimization. Luckily, we have a closed form solution in this last equation. Okay, so that's how we optimize the linear regression model. Right. So for clustering, we also have, yeah, we can see the same logic applies here. That we want to infer a function f from x to y. Okay, but now we don't have y to guide us how to actually adjust model parameters. Okay, there is no correct output, and hence this is unsupervised learning. Okay, the training is actually guided by implicit measure on how well these clustering function perform on data. Okay, for example, we might have an assumption that the cluster should be compact, and as such, data points should be close to the center of the cluster that they belong to. Okay, it is more challenging task, but it is also useful for discovering new cluster or groups of data, which we might not aware of. Okay, so this is the example of learning K-means clustering. Okay, we have this objective, which is to measure the difference between the distance between xi and its the center of its current cluster. Okay, so this should be minimized as much as possible. Okay, so mu are the cluster centers. The optimization as k-means has been devised to is to iteratively reassign x to the closest mean cluster. Okay, so that's correspond to adjusting the zi. Okay, move x to the cluster which is closest to x. Okay, and adjust its assignments. Okay, and once we've done with this step, we move on to the next step, is to readjust the mean of the cluster. Okay, and by repeatedly perform these two steps, we then it can be proved that it minimizes this objective function. Okay, so this is k-means clustering. Okay, now as you can see that in whether classification, regression, or clustering, it involves having the objective function, okay, write down, and then we want to optimize that objective function in some way using some optimization algorithm. Okay, could be a calculus or some algorithm that can be proved to minimizing this objective or loss. Okay, right. Of course, from just the model, we can also add some constraints to the model. Okay, so I would say this is particularly useful for the case where we have prior knowledge about data. Okay, for example, we have some knowledge that not all the features are useful. We can use feature selection regularization and incorporate it into, say, for example, logistic regression, so that the majority of W would be 0. And by having 0 value W, meaning that we don't consider that feature in our prediction. Okay, so regularization is useful and is one way to incorporate constraint into the model. So it's often in this form. We have the main objective, could be the loss function that we have discussed earlier, plus some regularization term, okay, weighted by some regularization parameter, lambda. Okay, so this controls how the strength of the regularization. If lambda is 0, we reduce to just the main objective. But if lambda is non-zero, oh, by the way, lambda is non-negative from 0 to 1, okay, by convention. So if lambda is not 0, then we are imposing some regularization on the parameters of the function. Okay, and these two combined results in regularized objective. Right. Okay, so this is one example, just to see how it works in practice. Say, for example, this is the log loss that we have seen for logistic regression. Okay, and this second term is actually the L1 regularization. Okay, what it does is just what sum or the magnitude of the components of W, okay, from 1 to m. So where m is the dimensionality of the data or the number of features. Okay, so while we're trying to minimize this, but if W is the magnitude of W is large, okay, or the sum of them is large, then it counters the minimization of these, right? And so in order to minimize the whole thing, the sum of Wi should be as small as possible, okay? By having small sum of Wi, meaning that the majority of W would go to 0, okay? As indicated in the right figure with L1 regularization. So the x-axis is actually the value of Wi. As you can see, the majority of the values are 0. Only some Wi is not 0. Okay, so in effect, this actually helps us filtering out redundant features. Okay, because this Wi will be multiplied to xi, right? And the component of Wi, which is 0, would just multiply to whatever features in the x vector, and the result would be 0, meaning that we don't consider that feature in the prediction. Okay. Yes, this is because sparse solution. Okay, so only a few of Wi is non-zero. Whereas we can also use L2 regularization. So this would change from sum of the absolute function of Wi to sum of Wi square. Okay, and when we use L2 regularization, it just constrain the value of Wi to not having large magnitude only without being sparse. Okay, so this is the result of learning logistic regression with L2 regularization. Okay, and the whole thing is the new regularized objective. And as you can see, if we set lambda to 0, it means that we turn off the regularization part. Okay, and it reduced to the normal objective function. Okay, right. So linear regression can be, you can also incorporate regularization into a linear regression. Okay, for example, this L2 regularization would produce the model which we call rich regressor. Okay, and the solution changed to this as compared to the previous one. Okay, I think I'm running out of time, but no worries, because we're almost at the end. All right, so so the next important thing is, how do we evaluate the model? Okay, the thing that I would like to point out is that, first of all, learning is not memorizing. Okay, we expect that the model be able to generalize to unseen example. Okay, it would be easy to construct a model which perfectly explain the data, the training data, let's say. Okay, but it fails to explain unseen data, in which case we call we say that overfitting occurs. Okay, so one way of construct this perfect model for training data is just to memorize, right? Okay, you store everything, every pattern in your memories, and then if you see the pattern you have seen before, you can actually predict its class level without difficulty. okay, but it does not generalize to new data, which slightly different pattern, okay, but from the same class. Okay, what we care more is generalization ability, okay, the ability to be able to predict new data with high accuracy, okay, unseen or novel examples with high accuracy, okay, and the way that we want we can measure generalization probability, generalization performance is that we need to probably simulate our data, okay. We often divide the data set into training and test data set. We train our model or adjust our model's parameters using training set, and then we test the model, okay, how it can correctly predict unseen test data that we has held off in the first place, okay. We have whole our method, or we also have careful cross-validation, okay, as visualized by the picture, okay. Yes, so that's probably the thing that I would like to stress, that I've seen students report training accuracy or training errors, okay, that is less interesting to me than the test accuracy or test error itself, okay. We're more interested in how well it performs on unseen data, okay. This is the way we should measure the performance of the model. Right, so I probably end this session with some challenges in machine learning, okay. First of all, high dimensionality of the data, class imbalance. I guess some of you may have seen this problem. Noisy labels, okay. In supervised learning, we need labels, but if labels are noisy, then we learn the wrong we learn the wrong relationship, okay. And lastly, probably the change of data distribution itself, okay. Solution change in time, okay. How do we deal with that, okay. I'll just throw in the keywords without being super detailed about these challenges, okay. Some of which are still ongoing challenges, okay, and then probably you will be able to contribute somehow, okay. Right, so so the first challenge is dimensionality reduction, okay. If we have more feature, naturally we need more data to cover the space that the feature spans, okay. And obtaining more data probably not always possible, okay. And one way to mitigate the problem is to try to reduce the number of features, okay, based on some assumption that some of the features are irrelevant to the task, okay. The intrinsic dimension is much less than m, where m is the number of features, okay. And we want to select only k informative features out of m features, okay. And this is essentially dimensionality reduction task, okay. It can occur as a pre-processing step, okay, or it can be like L1 regularized logistic regression, okay. It can be built into the model, okay. Some famous example, okay, filtering, PCA, okay, principal component analysis, or it's random prediction, okay. Class imbalance problem is also huge topic nowadays, because real world data often imbalanced in nature, okay. We see some class of star more often than the other class of stars, okay. And so how we when we have imbalanced data, okay, our model tend to be a little bit biased to the majority class. So how we do that? We might consider undersampling the majority or oversampling the minority, or we can weight the instance. Okay, instance from the majority class will get less weight loss. Okay, if you do wrong on majority, it's not going to be a huge problem. But if you do wrong on a minority class, then you would incur a huge loss. That's how we treat using instant weighting. Okay, so this is just example of majority undersampling. You try to reduce the blue majority classes so that it has they have roughly the same proportion, as opposed to sampling minority class. Okay, you generate new examples in green classes so that they would end up having similar proportions, right? Noisy levels and features is also a problem, okay, because you teach the model wrongly. Okay, this is clearly a problem. Okay, how could we deal with that? We could model the generation of noise. Okay, how noise occurs. Okay, we can pre-process by removing some outlier. Well, there's a subtle distinction between outlier and noise, but generally speaking, you might consider removing some suspect instance. Okay, you can use regularization to avoid overfitting, because when models learn from noisy level, it means learn from it overfit to noise without being able to generalize well to non-noise data. So avoid overfitting could be useful here. Okay, and when data distribution change in time, or in machine learning we call concept drift. Okay, that probably require us to detect when does the concept drift occur, and we probably need to relearn the model, or we can use online learning algorithm to learn from the data in real time, okay, without training and testing phase. Okay, once we got new data, we adjust the model. Okay, this is online learning, right? Okay, so lastly, okay, sorry, it's almost 18. So the big picture of machine learning is, this is concerned with application of machine learning to whatever task you might have. So first know what you want to do with data. Okay, what input you have, what output you want. Is it supervised or is it unsupervised? Is it classification, regression, or clustering? Okay, and then you pick or select or build a model aiming to capture the relationships in your data. And then you devise an algorithm or use existing algorithm to optimize the model in order to minimize the loss. Okay, the first step would be to test your model empirically, okay, using the data. Or if you can do theoretically, in theory, okay, you can show that your model will work on any kind of data of the same kind. Okay, so this is the in machine learning is the generalization error bound on the performance of your model. Okay, so these are more or less 5 steps involved in applying machine learning to the data. Okay, right, summary. After this an hour or so time, I hope that you should be able to answer these questions. Okay, what is machine learning? What are the difference between supervised and unsupervised? And of course, what are the major steps in the ML process? Okay, and I guess that's for me. Thank you, everyone. And if there is any questions, you are welcome to ask.
Thank you very much, Dr. Jakramate. So students, any questions? Okay, so we have one from Arifin. Maybe please switch on your video and you can ask the question.
Hello, am I audible?
Hello.
Okay, can you hear me? Yeah.
Yes, yes.
Okay, great. Thank you for the lecture and for the opportunity to ask questions. So I'm curious because, like you said, machine learning have the input of data. Like the data is the important aspect that the machine can learn from. But there are so many cases from astronomy, like you also said, there is not much data coming from. So is there I don't know, a trick rather than augmenting data, because you have current data, then you can augment to make it bigger, the data set. But is there a computational trick other than augmenting to simulate probably the data variability? Yeah, that's it. Thank you.
Yes, I guess I think your question might relate to this. Sorry, if I could go back to this oversampling. Well, this is just for one class, but you can also sort of apply this idea to generate data from all classes. So the most basic idea is that you can see from this picture that they try to link the two instances in the same class and then generate a new data in the middle. Okay, and if you repeatedly perform this oversampling, you probably end up with new data. But there is also concern, as you might imagine, that the question is how legitimate this red data is. I mean, is it actually the data that we will observe from this class, or is it just artificially generated data? This is a big question, and well, I guess it's difficult to answer if it's difficult to verify for sure if the newly generated data is actually is valid. Okay. So apart from that, if it's an image data, okay, in deep learning, people do the same image. They do rotation and flipping, okay, and shear the image so that it generates a similar image. So I guess that's the similar idea to this oversampling technique, and in practice, people do that, and it works quite well in real world. So so yeah, I'm not sure that answers your question.
Thank you, but I might have a second question. So
sure.
Is that okay? Yeah.
Okay. Yeah.
Yeah. So that's regarding for probably varying the data by, like you said, augmenting, rotation, and shear. Is there a way to, how to say this, but to evaluate? Because I've read some papers, let's say, to detect gravitational lensing, let's say, from this data set. They say, oh, we use this method, we use B method, and then the performance is good. But how to check whether the performance is really good? Is there, should a standardized test being implemented or being introduced to the ML in astronomy? Or yeah, how to measure, how to benchmark the performance of a machine learning system? Is it rather than evaluating from accuracy or accuracy and the other metrics? So I'm curious. Thank you. I hope the question is quite clear.
So So you mean evaluation of the data generation itself, or the, I mean, for the whole process, it should end at the accuracy. Meaning, if we want to predict something, the ultimate goal would be to build a model to be able to predict unseen example as accurately as possible. Okay, and the generation of training data, if it helps in the process, it would contribute to the improved accuracy. But if the data that you generate does not actually produce meaningful patterns or corresponding to the true data distribution, then your final accuracy would suffer. Okay, and I guess that's I'm not sure if there is any more direct way to measure the whole process, apart from measuring the final thing that you would like to achieve. Okay. So, yeah. Okay, could you, yeah.
Yep. I think that's good, because it's, again, we could be biased from the data set, because the accuracy only measures our data set, the model and the data set, right?
Okay, right. So so the bias would occur in case that your label or answer is also noisy. Okay, but if you, as always, if you take time to curate your test data, or make sure that your test data is accurate, and it reflects what you really want in the end, that would be, well, I guess it would be good. Evaluating the model on the test data that you have checked already, that would be one good performance evaluation already. So yes, I don't see why should there be any bias in that process. Yeah, so so not sure if
yeah, I think that's enough. Thank you. Yeah, thank you very much for the answer and the guidance.
Okay, welcome.
Thank you, Arifin. So we have 2 minutes left for this session before we move on to the breakout session. Is there any other participant who would like to ask a quick question, a short question? I would take that as a no. So maybe can I ask here for the organizer to prepare to move us into the breakout room, maybe 1 minute earlier. Maybe there the participant would have more chance to ask some questions later.
Sorry, Ira.
Yes.
Do you need breakout room to?
No.
Oh, you mean break time, yeah?
Yes.
Okay. Yes, sure. But before we have break time, we need to take a photo.
Oh, all right. Okay.
I just needed to ask one question. Can I ask? Sorry for the delay.
Yes.
Okay. So
who's that? Can you switch on your question, your video?
Yeah, sure.
Okay, please go ahead.
Oh, your microphone.
Praveen, you need to switch on to unmute.
Okay.
Right.
Yeah. Am I audible?
Yes, yes, we can hear you.
Yes.
Okay, okay. Yeah, this is related to global fitting actually, and more or less not much related to astrophysics as per se. Actually, I was thinking, can we have, like, I have a bit of 4 equations, like 4 different parameters are there, and I want to global fit them. And is it possible to use machine learning to create equation so that I could global fit it and without over parameterizing the whole thing? Is it possible that it directly gets the equation as possible and creates some sort of?
Yes. So I think your problem belongs to what they call multi-objective optimization, and I'm not sure if there are any trade-off between those objectives. Like, can you actually globally optimize the 4 models altogether, or does it, like, if you improve something, the other thing would be going down? That's more challenging. And yeah, if you want global, well, global here is quite, unless it is linear regression, you can prove that it is convex. The global objective function is convex, then you will reach global points, globally optimal point. But if once you have combined them and it produces non-convex, as in neural network in general, so you have many hues and values, okay, and you don't really know for sure which is global. You only have, you will reach local, okay, and that's the difficult part of convex, non-convex optimization. And the best we can do is that we could restart the optimization several times, okay, and observe which of the time give us the best objective function value, okay, and we can assume that that's probably be the global or near global thing that you would get. Or you can switch to people in evolutionary optimization do this a lot because they often deal with highly non-convex function landscape. And yeah, so the essence of evolutionary computation is also relies on randomness and repeatedly sample the solution and repeat the optimization several times, so that in the end, hopefully you will reach the best possible point in the solution landscape. Okay. Yes, I think, but for back to your problem, if you are concerned with linear regression, even though you have 4 of them, you can combine them into a single objective function, and then you can do normal optimization, and I think you will reach the global optimal points. Okay.
Thank you, Professor.